Okay, fine. So today we will start the topic, so bias variance trade-off, and how we can represent this bias variance mathematically. So before start this lecture, this bias variance, the definition of the bias and variance. So let me first explain the two important concepts. It's very simple, although uh, one is the population and another one is the sample. So population means that entire data set, means population, entire data set, entire population means uh, suppose suppose I want to uh, uh, calculate the average salary of an Indian people, especially who are working in the IT industry, average salary. Okay, so all the Indian people, especially who are working in the IT sector, so I want to calculate the average salary of Indian people. Okay, so in real life, it is not possible to calculate the average salary because I don't know the exact people, exact person, exact human being, the working who are working in the IT industry. Okay, so this you may consider is a population. It's a population data set. This one just you consider the population population data set. Okay, so how we can calculate the average salary? So now this data set is come into the picture. So in this one, I will consider some diversify the data set. Diversified data set means I will take some of the people who are from the this north side. Okay, some of the people that I will take who are working in the south side, based on based on different age group, then different gender, okay, different religion, different gender. So let's say we have 10,000 people who are working in the IT industry, and I will calculate the average salary of these 10,000 people. Okay, so in that way, maybe I can somehow just calculate the tentative average salary of an Indian people. So this will be my sample data. This one is my sample data set. Correct. So sample and population, this one is a population data set. So um, I will never get this population data set. So, but through this sample data set, I can just calculate the average salary of an Indian people, especially who are working in the IT industry. Okay, so now come to this uh, bias variance part. So the point is, let's say this one is this is my model. Okay, this based on the population data set. This one is the kind of graph, okay, based on the population data set. Correct. Although I never this achieved this population data set, but just you assume this is a model based on the population data set. Okay. And my sample data set. So let us consider out of 10,000, let us consider out of 10,000, suppose 1,000, based on this 1,000 data set, data point, based on 1,000 data point, the model actually draw one line. This one is a linear regression line. This one is based on the sample data point. Sample data point. Okay. If I consider, suppose different 1,000 people, okay, and if I draw the another one more this linear regression line, so maybe this one is another one based on different 1,000 people. Okay, now third again, let's say for third one, that is this one is again, that is 1,000, sorry, based on the 1,000 people data point. Okay, so these three are my sample data point. This one sample 1, this one is sample 2, and this one is sample 3, and this one is my population. Okay, so I want to achieve this graph. I want to achieve this graph. So now point is the bias. Okay, the definition of the bias, it is the, now the definition is, it is the inability of my machine learning model to fit on the training data. Okay, so in this case, this sample 1, sample 2, and sample 3, so in this case the bias that will be very high, bias that will be very high. Clear? So bias that is very high, bias high means, bias high means it is the kind of inability of my machine learning model to fit on the training data. If my model does not capture the pattern of my training data, that is the high bias. Okay, so now can you correlate this definition with this example? Sample 1, sample 2, and sample 3, and this one is the population 1. So in this one my sample 1, okay, this one is my sample 1. So that is the, this one, this model means my model gives me this linear regression line. So that is a high bias. So if the machine learning model does not fit properly on the given training data set, that is a high bias. That is a high bias. And if my machine learning model fit properly on the given data set, then it's a low bias. Then low bias. Low bias means if my model capture the pattern of the training data, then low bias. So now the model are not able to predict any pattern of the given this data set, so they are very far away from this population data set. Okay, so now I hope this high bias and high bias and low bias, the definition is clear to all of you. High bias and low bias. Now come to this variance. Variance is means how much change in the prediction, how much change in the prediction of my machine learning model when we change the training data set. When we change the training data set. So now you see, in this case, sample 1, sample 2, and sample 3. Okay. Now my training data set, first sample is this one, 1000 data point. Second sample, that is different 1000 data point. Third sample is again different 1000 data set. So how much change in the machine learning model if the training data set is changed, that is a variance. So now you tell me the variance is high or low in this case. In this case, variance is high or low? The variance is low. Variance is low. Because here I change the data set. Okay, I change the training data set. The variance is very little bit. The variance is, the change is very little bit. Clear? So the difference in the result of all three regression line is very less. Clear? So now let's say in place of this linear regression, let's say I applied some polynomial linear regression. In place of linear regression, now I apply the polynomial linear regression on this sample data point. I apply this polynomial linear regression on sample 1, sample 2, and sample 3. And the degree is, let's say, that the degree is, let's say, 50 degree. Okay. So this was my population. Okay, based on the population data set. Now I change the algorithm, and in place of the linear regression, now I apply this polynomial linear regression of degree 50. Okay, so now degree 50. So see, this is my, let's say, the population data set. So now if degree is 50, now clear. So this one is the one sample. Okay, now if I consider the sample number 2, this is a sample 1, let's say sample 2, let's say sample 2. Now okay, now here the bias that is very high, the bias is very high, sorry, bias is low but variance is high. Bias is low because bias is low means my model actually capture all the pattern of this training data. Okay, so in this case the bias is low, but variance is high. So my model is good on our data, the sample one data. Okay, but the moment you change the training data, the result is not as good as before. This is my high variance model. This is my high variance and low bias model. This one. Okay. So now come to this. Now I hope this bias, high bias and low bias and high variance and low variance, that is clear to all of you. I hope. Up to so far, if you have any doubt, now please ask the question related to the high bias, low bias, and high variance, low variance. Okay. So now come to this next part, that is overfitting. Overfitting. So now overfitting, generally this high variance model are overfitted. This high variance model, high variance model are overfitted. Means overfitted means on training data they are performing very well, but new unseen data they are not good. Correct? So that is overfitting. That is overfitting. So high variance is closely this related to this overfitting. High variance, high variance and low bias. High variance and low bias, that is the overfitting. Now underfitting. Underfitting means that is high bias and low variance and low variance. Means underfitting means my model does not pick the pattern of the training data, means that is the inability of the machine learning model. So that is the inability of the machine learning model, that is the underfitting. So this underfitting, that is closely related to the high bias. Okay, means not perform good on the training data also. So but ideally low bias and low variance model that we want. Low bias, ideally low bias and low variance. The model that low bias and has low variance that we want. Means low bias means on training data the model is good. Low bias means on the training data the model is good. And if you change the training data and on the new data set, if the result is consistent, that is low bias, low variance. But it is difficult to get both the low bias and low variance. Okay, actually the moment we decrease the bias, the variance increases, and the moment we reduce the variance, increase the bias. So just you remember this curve. I hope you must have seen this curve also. This one is a bias. Okay, this one is a bias curve. This x-axis is the model complexity, and this y-axis, that is the error, and this one is the variance. Okay, so this side is underfitting. Underfitting means high bias, low variance, and this side is, that is overfitting. Means if simple model means like, means here the model is simple, means like linear regression, linear regression. So as we have seen here, this one linear regression, okay, and this one is a polynomial this regression. So now here the polynomial regression with degree 50. Okay, means if you increase the degree, so that is a model that will be complex. Here the model that will be simple. Okay, so that's the underfitting, and this one is the overfitting. So just you remember this curve of this bias and variance and error versus model complexity. So here are some questions. First question is, how would you define the bias and variance mathematically? And second is, how bias and variance are related to overfitting and underfitting mathematically. Okay, so now first question is, how would you define this bias and variance mathematically? Okay, and this how it is related with the overfitting and underfitting in a mathematics term. So first, that is this mathematical intuition of this bias and variance, formula of this bias and variance in terms of this expression. So the answer of this question is, first let me just explain the expected value. Expected value. Okay. So expected value, that is represent average outcome. Expected value is, that is average outcome of a random variable, over a large number of trials, over a large number of trials or experiment. Okay, so in a simple sense, so expected value of a random variable, okay, is the kind of the average, means value of the repetition of the experiment. Okay, so let's say for example, so what is the average outcome if you roll a dice, let's say 1 lakh time, if you do an experiment, okay, 1 lakh time, let's say you roll a dice 1 lakh time, then what is the average outcome of this experiment? So this die has a 6 side, so now expected value that will be 3.5. That is a average outcome. Average outcome means if you roll a dice, let's say 10 lakh time, or let's say 1 crore times, okay, the average outcome that will be 3.5. I can prove this also, 3.5. Okay, or you do the same this experiment in a Python. Okay, there also you will get the same result, 3.5. So this expected, this value that is represented by this E of X, where X is a random variable, and E of X, that is a expected outcome, expected value. Okay. So here this X1 is the outcome. Okay, let's say that is 1, 2, 3, 4, 5, 6. So these are the expected outcome. So this X1 is 1, this X2, this X3, this X4, this X5, and X6. Okay. And the probability of this outcome, this X1, so that is a P of X1, and X2 plus X2 into my probability of X2 plus X3 into my probability of X3 plus X4 probability of X4 plus X5 probability of X5 and plus X6 probability of X6. So now X1 is 1, probability of X1, that is 1 by 6. X2 is 2, probability of this 2, that is 1 by 6. 3, 1 by 6. 4, 1 by 6. Plus 5, 1 by 6. And plus 6, that is 1 by 6. Now if you take this 1 by 6 common, so the 1 plus my 2 plus my 3 plus my 4 plus my 5 plus my 6. Okay, so now 1 by 6 into 6 into my 7 divided by 2. So now that is 3.5. Clear? Let me take one more example. So let us say we have 6 number. This example number 2, let's say we have 6 number. 6 number, let's say 5, 3, 4, 5, 3, 5. Okay. And mean of these 6 number, mean of this 6 number is, so 5 plus my 3 plus my 4, sorry, 4 plus 5 plus 3 plus 5 divided by 6. Okay, that is a mean. This one is a mean. So mean that will be now 8 plus 4, 12 plus 5, 17 plus this 25. So 25 by 6, that is a 4.1. Okay. So now can you do like this one? That is 3 multiplied by 5 plus 2 multiplied by 3 plus 1 multiplied by 4 divided by 6. Can we do like this one? So 3 by 6, 2 by 6, and 1 by 6. Okay. So 3 by 6. Okay. So 3 by 6. So this one is a x1 and px1. So x1, p of x1, x2, p of x2, plus x3, p of x3. Okay. And that is again, that is same, that is 4.1. So this one is expected value. This one is expected value. And this one is mean. This one is mean. And this one is expected value. So mean and expected value both are same. Okay. But here this expected value, there is a one important line here. This expected value is population mean. Is population mean. Expected value is a population mean. Actually, we cannot identify or find out the this population mean. Okay, we cannot find out the average salary of India population, but we can find the population mean through this expected value. Clear? So this expected value is x of I, p of x of I, that is summation I is equal to 1 to n. In case of continuous, that is x of I, p of this f of x of I into d of x. So expected value is the population mean. Okay. So in the previous example, so we cannot find the average outcome. If we roll a dice of, let's say, 1 lakh time, so how do we get the average outcome? How do we get the average outcome of the population? Suppose if you do experiment of 1 lakh time, or let's say 10 lakh time, so how do we get the average outcome of this population? So answer is this expected value. This one. This one. So this E of x, that is expected value, is population mean. Is population mean. Okay. Now come to this variance. Come to this variance. So up to so far, if you have any doubt, then please you ask any question related to this expected value and this mean. Okay. So now variance of this x, okay, means variance of this population, means variance of population. So variance of the population x is E of x square, expected value of x square minus may E of x and square of this one. This we will prove. This we will prove. Okay. Now you tell me the definition of this variance, or definition or mathematical expression of the variance. How we can calculate the variance? X of I minus my x square 1 by n, I is equal to 1 to n. Okay, this is the representation, this is a mathematical, this representation of this variance. Xi minus x square, that is a mean. This one is a mean. Square of this one divided by 1 by n. So if I'm writing, let's say, this x random variable in place of this xi, in place of this xi, okay, so this x minus this x square, that is a mean. So can I write like this one? Okay, and summation, okay, summation and this 1 by n, this whole, this represented by this E, expectation, mean. So that is E of this square. So can I write this expression from this definition of this variance? Both are the same. So this xi means this capital X, that is a random variable, and xi, that is the outcome. Okay, and x bar, that is a mean. This one is a mean. Okay, although this x bar is a sample mean, x bar is a sample mean. So in terms of population, the meaning of this average is the expected value. Okay, so E of x and square of this one, as square is here, and this summation and this one, this is represented by this E. expected value. So now this E of this x minus E of x and square of this one. So can I open this E of this x square minus E of x square minus 2x E of x? Okay, and here this expectation of this x plus y is equal to this expectation of x plus my expectation of y. So expected value of sum is sum of the expected value. Okay, so now E of this x square minus E of this expected value of x square minus expected value of this twice of x of E of x. Now E of x square, that is as such, minus this E of this is, let it be as such, minus this E of 2 E of x and E of x. Okay, so expected value of constant is a constant itself. This will be 2. Okay, and this one, so E of x square minus this, sorry, plus sign, so plus, yes, plus. So E of x square minus 2 E of this x and this E of x. Okay, so E of x, that is x is, let's say this x is 2, then expectation of this x as per this formula, that is 2 multiplied by 1, that is equal to 2. Okay, so E of 2 is equal to 2. So the expectation of this constant is constant itself, so E of x is here. So now E of x square plus E of, that is E of x square minus twice of this E of x, that is square, and this E of x, this is the constant, and square of the constant again constant, and expectation of the constant again the constant. So this can I write E of this x square plus this E of x square minus twice of this E of x, that is square. So that is equal to E of x square minus my E of x, that is whole square. So that is a variance. That is a variance. So now we have two formulas. So variance is equal to E of x square minus my E of x, that is whole square. Now second formula is expectation of, as per the definition, E of x square, and third one, that's both are the same. So summation 1 to n I is equal to 1 to n x of I minus my x of square, this one. Okay, so now the point is, what exactly are the bias and variance? It's mathematically means we can we express this bias and variance this mathematically. Okay, so there's a variance. Now come to this bias part. So now bias. So let us say we have, let's say, given the regression problem. Okay, so just you try to understand this. this one is a, let's say this one is a regression line. So up to this variance, if you have any problem, any doubt, then you please ask. Okay. So now this one is a, let's say this regression line, this based on this regression line, this based on the sample, based on this sample data. Okay. And so this is a true line. This is true line. Okay, based on this population data. Based on this population data. So this line actually we cannot see because we don't know the population data. Okay. So this regression line that we have, this regression line that we have. Okay. So now if we make, let's say 100 regression line, now just you try to understand the concept. If we make 100 regression line, 100 regression line based on the 100 different sample data set. Okay. Then this, let's say this f dash x, f1 dash x, let's say this f2 dash x, f3 dash x, likewise that is f100 dash x. Okay. And calculate the expected value. So E of this f dash x. Okay. So for 100 different data point, so we can plot easily the regression line. Okay. So there will be 100 different m value. This one, this one, this one, this one, this one, let's say. Okay. So that is E of this f dash x. Okay. And this f of x is, this one is f of x. F of x is, that is a true line based on the population. Based on the population. Clear? So if we calculate the expected value of different 100 regression line, that we will come close to this f of x. Okay. If we just calculate the average of these, let's say 100 line, so maybe we will close to this straight line, this true line, and this one is a population data. Okay. Now bias is, now just you see, this bias is expectation of f dash x minus my f of x, where f of x is a line, it's a true line based on this population data, and this one is E expected value of this 100 different line, that is a E of f dash x. So if we calculate the expected or mean of different f dash x, then it will be equal to f of x. Means that bias that will be zero. That bias that will be zero. So this one minus my f of x. So f of x is the population function. Clear? So this one is a bias. This one is a bias. So variance So in the context of this machine learning and statistics, this variance actually refers to the amount by which the prediction of our model that will change if we use a different training data set. Okay, means how much change in the prediction for a given point, okay, vary between the two different realization of the model. That already that we explained here, discuss here. This is the variance. Yeah. How much change in the prediction of our model when we change the training data set. Clear? So now variance, that is E of this f dash x minus E of f dash x and square of this one. Clear? So if this value is high, it means if we change the data, the performance that will change a lot. Okay. So there is a one simple Venn diagram of this bias and variance. So now you just tell me, there are four kind of diagram. So here this is low bias and low variance. This is the low bias and low variance. Okay, means if you change the training data set, the performance that will not change a lot. And here the bias is also low. Bias is also low. Clear? So this one is low bias and high variance. This one is low bias and high variance. Now you see, bias is low, but variance is high. Variance high means this one, this side, this side. Okay. Low bias means sorry, variance low means this one. This one is high bias, low variance. High bias, low variance. Clear? And this one is high bias and high variance. High bias and high variance. Now is it clear to you? Hello? Okay. So now next topic of discussion is precision, accuracy, precision, recall, and this F1 score. Okay, so let us start this accuracy. Okay, so accuracy is number of correct prediction. Okay, that I will explain through an example. And total divided by total number of prediction. Total number of prediction. Number of correct prediction divided by total number of prediction. Okay, so let us say, for example, this actual output, and this one is a, let's say, output of logistic regression. Logistic regression is a classification problem or regression problem? Logistic regression. Now, please tell me, this logistic regression is a classification problem or regression problem? Very good. So now, Dr. Manju ma'am, it's the classification problem. So tomorrow that we'll be having a session on this logistic regression. Okay, at that time that we will see this logistic regression is a classification problem. Okay, so now actual output. So let's say this actual output is 1 0 0 1 0 1, and this logistic output, okay, let's say 1 0 1 1 1 and 1, and decision tree output, let's say this 1 1 0 0 1 1. Okay, so now as per this definition, number of this logistic regression, okay, this logistic regression output, this decision tree output, okay, this one is the actual output. So here number of correct prediction, so here correct prediction, this one is correct, okay, this one is correct, now this one is correct. So now this 4 by 6 accuracy is 4 by 6, that is 0.66, means 66%. Here this one is correct, this third is correct, now this one is correct, so that is 3 by 6, that is 50% accuracy. Okay, so this one is for binary classification, this one is for binary classification. Okay, actually this one is a classification matrices. Okay, regression matrices is mean square error, RMSE, okay, root mean square, R2 score, adjusted R2 score. These are the regression matrices. This one is the classification matrices. Classification metric. Okay, so in the classification matrix, accuracy is there, precision that will be there, recall, F1 score. Okay, so these are coming under the classification. So this one is a binary classification. So same way that we can do in a multi-class classification also. Okay, so in the multi-class classification, that let's say the actual output here, let's say the actual output is 0 1 2 0 1 2 3, let's say this one is the actual output. Okay, and the same this logistic regression, okay, the output is 0, let's say 0 2 0 1 1 2, let's say. So as per the definition of accuracy, number of correct prediction divided by total number of prediction. So this one is a correct prediction, this one is a correct prediction, correct one, correct one. Okay, so now this 4 by 7. Clear? So this is a kind of accuracy. Clear? So now here the definition is very straightforward. This number of correct prediction divided by total number of prediction. But there is a disadvantage. Okay, there is a disadvantage. So before coming to this disadvantage of this accuracy, okay, so let me first explain the point how much accuracy is good. How much accuracy is good. Yesterday, one participant that has asked this question, how much accuracy is good? Yes, tell me. How much accuracy is good? Hello, 80%. Okay, so let me explain this point uh, with the help of this example. So let's say case one. Let's say case one. Okay, so there is a one model. This model takes the input as an X-ray image. X-ray image. Okay, and our model based on this X-ray image that will say, okay, the patient is suffering patient is suffering from a disease or not, or suffering from a cancer or not. Okay, so by showing an image like X-ray, our model that will say, let's say out of 100 people, let's say 99 people that will correctly examine by our model. Okay, so 99 out of 100 means that is a 99% accuracy. So 99% accuracy means that is out of 100 people, the 99 people that will correctly examine by our model, but single, that is one person, okay, the model shows the false detection. One person on one patient, okay, that is a false detection. So we cannot deploy this model in a hospital. Okay, we cannot make this mistake in a real life. Although the accuracy is, see, 99%. So we will not deploy this model, even though the accuracy is 99%. Now, case two means after, let's say, after seeing the behavior of a particular customer for this whole month, okay, so the model that we want to actually predict that the person will order the food on this weekend or not. That is Swiggy, let's say Swiggy example. Okay, so based on the behavior of the this, or based on the last month order, okay, so the model that will predict the person that will order the food on this weekend or not. So here even the accuracy is 80%. Okay, means 80% accuracy. So you can deploy the model. Meaning is there is no such big loss. Clear? So you can deploy this model. You can deploy this model. Only 20% this mistake is doing by this model. Okay, so accuracy is 80%. So you can deploy this model. There is no such a big loss. But here the accuracy is 99%. Now, Can you relate this example 1 and example this case 2 with this heading? This how much accuracy is good? So the point is, it depends on the application. It depends upon the application. Means you cannot say this 92% accuracy is sufficient. Okay, means 95% accuracy is sufficient or 80% accuracy is sufficient. If you get suppose 80% accuracy, okay, and this 80% accuracy is never achieved by any of the author, let's say in any of the research article, if suppose you get the accuracy 80%, okay, and this 80% this accuracy that is never achieved by any of the author, so that is perfect, fine, no issue. But suppose based on this your data, the accuracy let's say 92%, okay, and many author that has published the the same algorithm on the same data set, the accuracy is let's say 95%, then you have to improve the accuracy. Means that is this one is not sufficient, this 92% accuracy, because someone has does this the same this algorithm with the same data, that's 95% accuracy. Clear? So now the next point in continuation of this, the problem with this accuracy score, what is the disadvantage? Yes, so the question is how to increase the accuracy. So there are various hyperparameters, okay, so let's say very basic example is uh, this linear regression, or let's say this knn, okay, just you vary this k value, okay, in case of linear regression just you vary this m and b, okay, in case of regularization just you vary this lambda, this hyperparameter, okay, this gradient descent, okay, this is the optimization. So just you change the this hyperparameter accordingly, you will get the different accuracy, and once you achieve the maximum accuracy, okay, so means we have to be play with the hyperparameter. Clear? So now the problem with this accuracy means it gives us only a number, this 80% accuracy, 90% accuracy, 92% accuracy, it gives us only a number, okay, but it does not tell the type of mistake. It's very important, type of mistake, type 1 or type 2, type 1 or type 2. So means there are two type of mistakes. For the first mistake, the patient that was suffering from a disease, but our model says he has no disease, okay. Second mistake, the patient that was not suffering, okay, but our model says the patient is suffering from a cancer. So accuracy score that does not tell us how much the first mistake that has happened and how much the second mistake that has happened. So our accuracy score that will tell us that a mistake that has happened. So 90% accuracy means 10% time a mistake has happened. But the first mistake or the second mistake, this is not told by this accuracy score. Okay. So this problem is solved by this confusion matrix. This problem is solved by this confusion matrix. Okay, so now time is 4:10. So this next part, this confusion matrix, this recall, okay, and this F1 score. So this all this thing that we will discuss in a session uh, on this morning, this 8th May. Okay, 8th May. So now day after tomorrow, again my session that will be there. Okay, the first half. Okay, on 8th May. So there will be my session on 8th May, mean square error, MAE, RMSE, R2 score, adjusted R2 score. At that time that we will cover this uh, precision, accuracy, confusion matrix, recall, F1 score. Okay. So far, if you have any doubt, then please type here in the chat box. Yes, any doubt? Okay, okay, fine. Actually, there are various methods of fine tuning. So we will discuss in this FDP also. Okay, correct, fine. Okay, thank you. Take care. Okay, bye.